but we'll do a quick go around. So I'm Nathaniel W2NAF. Welcome to the Ham Site Telecon. Um, and just go round robin. Bill Engelke.
Bill Engelke, AB4EJ. Been working this week on further fleshing out of the NASA proposal we're working on for collecting all the data from RBN and WSPR and PSK Reporter and DX Cluster and all that, and putting that into the Madrigal database if NASA would like to do that, and with links given to them, of course. And also got a thing working for Case Western, so from their GRAPE stations, they can have an automatic job that runs at the end of the day, 5 minutes after the plots and everything are created, it uploads them by email to Box. So John is going to handle the distribution of that. He's got the stuff and he's testing it now. So back to Net.
Thank you. Mike Neruda, AA8K.
Michael Neruda, Alpha Alpha 8 Kilo. Greetings to everyone on the conference.
Thank you very much. Stephen, W2WF.
Yeah, Stephen, W2WF from Texas, just interested in WSPR and solar physics, everything that's techie and physics related. So that's it.
Thanks. David Kasdan, 88Y.
Greetings. I'm David, the faculty advisor of the Case Amateur Radio Club at Case Western Reserve University, and we appreciate the efforts of automating the data uploading for the GRAPE. I have to admit, I'm getting tired of the half-hour every Sunday evening task of doing all the uploads.
Wonderful. Thank you. Mike Eccles, nice to see you.
Yeah, good evening. Mike Eccles, can you hear me?
Mm-hmm.
Yeah, Mike Eccles, GM3 PPE from Scotland. I've just joined Ham SCI. I'm a retired astronomer and extremely interested in sporadic and ionospheric physics.
Perfect. That's wonderful. Bill Lyles, NQ6Z.
Greetings. So as you know, I'm NQ6Z, and lately what I've been working on is doing propagation to the troposphere modeling using a mechanical differential analyzer. So not Ham site type stuff.
So the
idea, you can make them with the vector sets, folks.
So the idea, Bill, once you get that done, we're going to take down our servers and everything, and we're going to replace them with your mechanical system, right?
Yeah.
Yep. We're looking forward to that.
Differential equations, just fine.
Yes. Our postdocs and grad students are very excited about this advancement. Dave McGaugh, N1HAC.
Hello, David McGaugh, N1HAC, research engineer at Dartmouth College, working on HF receivers on sounding rockets, VLF receivers on the ground, and God knows what else, magnetometers and all sorts of like. Back to Net.
And John, N8OBJ, we already heard. No, we did not hear from you yet.
Yeah, I got three. Let's see, 1, 2, 3 GRAPE stations shipped out this week. The development platform shipped out. I just got off with the 1 o'clock Zoom meeting with Jay Silber. I got his automation stuff. Well, the update installed on his thing, and I switched him over to 5 megahertz. Right now, I'm chasing after a bugger or a board for the GRAPE 1. I had a shorted MLCC cap that was difficult to find. And now I've got an oscillating 5-volt regulator. So once I get that going, then I'm done.
Nice.
Other than that, not much going on.
Thank you, Christina, KD8OXT.
Hey folks, PhD candidate from Case Western working on the GRAPE project. Also grateful for the automatic uploads. Let's see, what am I working on? We've got prep for the HamSci workshop. We've got a project with some GRAPE deployments. And some data analysis from previous experiments. And that's all what I'm up to these days. Back to Net.
Thank you. Dev, KC3PVE.
Hello, good afternoon, everyone. I'm Deb Joshi, KC3PVE. I'm working as postdoc with Professor Nathaniel Friesel, W2NAF at University of Scranton. So we're looking at job sounder observations for the Personal Space Weather Station, and trying to see if the detections that has been made could be analyzed to understand the characteristics of the traveling ionospheric disturbances. And I'm also in the committee to organizing committee of the HAMSci workshop. So that's keeping us busy. Thank you.
Thanks. Jim Farmer, KB4 BSC.
Yeah, Jim Farmer, kind of new to the group, just trying to get my feet wet, retired RF analog product design engineer, interested in time and frequency issues.
And let's thank you, Gary, AF8A. Hey, nothing heard. And Tolef.
Good morning, Tolef Winslow, KB7 DNS. Sorry, I don't know how to make Zoom tell me what it is, what the rest of everything is here, but just interested here in Houston. Thank you.
Great, thank you very much. And I think besides, did I get everyone except for Steve Serwin? I think so. Well, with that, just a reminder to everyone, this is being recorded and it will be archived on YouTube and made available through the HamSci site. So I'd now like to introduce Steve Serwin. He can give us an update, and he's also going to be our main speaker for today. So Steve, take it away.
Okay, is my audio coming through this time for real?
Sounds great.
Okay, well, I'm Steve Serwin, sort of semi, but not really retired institute scientist from Southwest Research Institute. I've been working on trying to analyze the Doppler shift data to back project what the change in the layer height ought to be. And it's looking pretty interesting. In fact, it sort of ties in with a bunch of the other stuff that we've done over the last few years. That's what I'm trying to tie together. So I've got a talk here today that's in the really rough stages, not polished, more like chainsaw stage. So any comments everybody has would be very, very appreciated. On the ham radio front, yesterday, I was heading down south to Dilley, Texas in my truck with the mobile rig on 20 meters, long about gray line time, and worked IK4 GRO, LARO in Italy. Got a 5.7 out of the mobile. That was pretty cool. So HF is still around. Are you ready to start, Nathaniel?
Go for it, Steve.
All righty. Let's see here. Makes it big, and that starts it. No, it doesn't. That starts it. Is that coming through?
Looks great.
Yep, looks good.
Okay. So what I'm trying to do is estimate the changes in ionospheric height from looking at the Doppler data, but I'm also going to correlate that with some of the other things that we have to include ray tracing and ionosons and time of flight measurements. So let me see if I can get this thing off so I can read my own screen. How do I get that? There, down there is better. Okay, we've got multiple data sets that include these Doppler frequency spectrograms. We've got some ionoson data. We've got some time of flight data. We've got some ray trace simulations, and we've got these on different days and frequencies and different events. So what I've been trying to do is tie these together and specifically back project from Doppler data what should be happening in the layer height. And also trying to put together a hypothetical model that might let us explain at least some of the observed Doppler frequency shifts, and if I may be so foolish and bold, to identify specific propagation modes associated with Doppler tracks that we see. I mean, if you never stick your neck out, how can you ever get it chopped off? So the data that I'm going to be showing is from the bipolar Doppler swings that we saw during the solar eclipse of August 21, 2017. This was data acquired by Steve Ryer, WA9V&J. We're going to look at also the positive Doppler shift and mode splitting that happened in the morning of the Festival of Frequency measurements on October 1st of 19, and also time of flight measurements on the January 29th. So basically, well, come on, can we not? There we go. All right, here's the, I guess I have to just click that button. It didn't work the way it used to with the up down buttons. Okay. Bipolar Doppler swings that WA9V and J observed. This is a path from WWV in Fort Collins, Colorado to WA9V and J's QTH near Milwaukee, and this was at 10 megahertz. Here's kind of the geometry. This is the path of totality of the eclipse. These kind of show you how partial or unpartial or full the eclipse was across the country. His path, here he is here in Fort Collins. Here's WWV and here's his location in Milwaukee. The eclipse actually crossed right over the propagation path. So it was a really good setup. And this over here that Christina provided kind of shows another geometric layout. Here's the more or less the path of the eclipse. Here's the propagation path. And here's the nearest ionosonde over in Boulder, which, as you can see, is considerably west of the center of the path of the apogee and quite a bit west of the QTH. So there's a timing issue that I need to work on some here, but anyway, that's the data we're going to look at. So the way we deduce refraction height profile from Doppler data, or at least in this case, was I took his graph, overlaid an estimated envelope of the Doppler versus time on it, added markers manually with a pencil to the curve at regular time intervals to make a dt delta time increment, and then imported, then to get the dy, made spots along the curve, and then imported that into a spreadsheet so I could do calculations. Then you can derive the average equivalent path velocity at each time increment because Doppler scales with velocity. Then you can calculate the relative change in the total path length by doing a cumulative sum integration. If Doppler is the derivative of path length change, then if you integrate path length change, you can get back to Doppler. You do need a GPSDO to do this accurately, because if you have a frequency error, that adds a constant velocity offset. And if you're going over a long time, it integrates to a big error. I took this data. Well, he had, I'm sorry, I'll show you data later on mine where I didn't have a GPSDO, but he did. And by the way, that spikiness that we've seen, Nathaniel, he has a note in his PowerPoint that says he's using a custom DSP operating on the Spectrum Lab data. So that may be where it came from, because I've never seen that on any of my Spectrum Lab data. So anyway, you can get the path length change. Now you have to define some sort of a starting height or a reference height from the ray trace simulation. And you use that with a geometric model, because the Doppler is a function of path length change. You have to use a geometric model, which includes, ground truth, ground distance between the 2 points, and a starting guess as to how high the ionosphere were, so that you can convert path length to height. Then you can add these, so you get a starting path length. Then you can add that starting path length to the relative path length change to obtain what the path length versus time profile was. And then you use that same geometric model to convert that into layer height versus time. So here's his data on the left. This is the raw data. So you kind of see a general high to low. This is over the whole morning. So down here is the morning transition. Middle of the day, here is the eclipse from about 1630 Zulu to about 1930. And this is the effect of the eclipse. Swings negative first because the ionospheric layer height increased. That was an increasing path distance, gave negative Doppler. Then it crossed through zero, and then positive as it came back down. So this, in other words, this outline of that is the derivative of the height change curve. And then over here is where it goes into the evening craziness. So here's how I got the data. I just sort of drew in by hand what that curve looked like to me, considering these as more or less peak detections. Then put some scale markers on here so I could get frequency or time hacks, and then measured what it was. So here's how it entered into Excel. So this is how it read indirectly. This is this curve in terms of frequency and Doppler shift. You can see it scaled from about minus 0.3 something hertz to plus 0.3 something hertz. At 10 megahertz, to convert this from Doppler shift to path velocity, you just multiply by minus 30. 300 divided by 10 is 30. That's the factor to relate velocity to Doppler shift at 10 megahertz. And so this gives you the path velocity in meters per second. And the minus sign is simply to denote that when the path gets longer, the frequency goes down. And then when the path gets closer, it goes up. Sign change, so 0.5 hertz is worth 15 meters a second. So then to convert, to compute the path length change through these Doppler numbers, or the velocity numbers, you do an numerical integration. So here's the path velocity, and so at each little increment of change in path, here's path down here and here's the velocity. At each increment of change, it's delta V times delta T. The delta V is the change in velocity. Delta T is over what time increment. And then to wind up with this profile, you do a cumulative sum. You calculate the first delta P and then add to that the next delta P and then add to that the next one and so on and so forth. And so here's the change in path length caused by this velocity curve. And it does what you'd expect. From a reference height starting at 0 here, here's the scale for that one, starts from 0. The path length changes by about 40 kilometers and then it comes back down. So that's what the path length is doing. Now you have to go to a geometric model to find out what that means actually in terms of H. And I used just a simple one, a flat earth geometry, perfect reflections at a virtual height, constant wave speed. So here's the two stations. Here's the ground distance. Here's the path that's changing. Here's the relationship for one hop. So once you know the path and the separation distance, you can calculate what the height ought to be. True, it's not curved earth, but you never see these models with symmetrical scale factors. This height is a few hundred kilometers, but the range is 1,400. So if you were to draw this in scale, this point would really be way down here. So bending that whole thing doesn't make a lot of error, but it makes some error. So this is one hop. Here's a model for 2 hops, and here's a model for 3 hops. And there's the relationship for each one of those. You can convert those to time of flight, easy enough using the speed of light. So here's 1 hop mode, 2 hop mode, 3 hop mode. Note that change in slope, which means that more hops ought to have more Doppler. And indeed, that's true. If you consider that if you have multiple 1, 2, and 3 hop modes and the height changes, they're all coming off, if they're all coming off the same layer, which isn't true always, but if they are, these modes are longer. This mode's longer than that one. This mode is longer than that one. You see the calculations. If the path changes the same for all of them, the longer modes have to have more absolute shortening in the same amount of time, which means they have more velocity. More velocity means more Doppler. Okay, back to V and J. So here is this path length change over the course of the eclipse. I'm sorry, this is the layer height change using that model. Using that model with the path length change, this is what you get for the change in the layer height. Now remember, this is change. When you do an integration process, it's always integral of such and such dx equals something, something, something plus c. Well, that plus c you don't know, so you lose a reference. All this is the change. So this curve, which is trying to give you height and absolute numbers, I had to get a reference point. And this is where I took Christina's movie and went in there and found out that at about the time of the start of the eclipse, the F layer was at 201 kilometers. So you just take this and add that 200, and here's what you get for absolute layer height over the course of the eclipse. So this is that model I'm talking about. We're working on a better way of getting it than pulling these frame shots out of a movie, because these may or may not have been at the right time. This predicted like a 32 kilometer change in height. We didn't get that same number on the other one, but there's so many things that could be different here. What we're after is a ray trace simulation that would tell us the height of this apogee versus time, because that way we could directly compare it with the other data. One other very cool thing to notice here. So this is a control day. Down here is the eclipse day. You can see that on the eclipse day, this apogee is higher than it is on the control day. I use this 201 from the control day as my reference, and it changes. So the eclipse, even in the ray trace, showed a definite change in layer height. For the F layer, look what happened to the E layer. Absolutely nothing. That E layer could care less that the eclipse came by. It did not change height at all. File that away in your database, because this is going to be a recurring theme in many, many, many of these data sets. And it's going to help us to know when we look at a spectrogram, which one came from an E layer and which ones came from an F layer. Because the F layers change, the E layer doesn't. And this happens over and over again with different data sets. So here is the ionoson data that Christina put together for me. There's two overlaid graphs here. The blue one here is the control day, the day before the eclipse. And this orange one is the eclipse day. Main difference is this hump right here. Now let's see if this is going to work. Yes, it did. So here is my computed delta H scaled with the same vertical scale factor. Here's 0, here's 100 kilometers. See how big that is? Here's how big 100 kilometers is on that scale. Likewise, I adjusted the horizontal scale so that the 1 hour tick marks down here exactly match the spacings for the hour marks down there. And that really isn't a bad fit. It pegged the amplitude very closely. The width, maybe not so much, but there was something else going on right here in the Boulder data that we didn't see in the eclipse data. But then they're not in the same place. The Boulder data is quite a bit farther to the west. And as far as relative timing goes, that I'm not so sure about. I know that they're in different places. You know, the sun certainly comes up over Milwaukee before it comes up over the apogee, before it comes up over Boulder. So you notice that even though these 1 hour increments or the correct width, I had to slew the thing in time to get it to line up. So this is something that bears some more study. But nonetheless, it's pretty encouraging. So here's the next data set. These are some positive Doppler shifts and some mode splittings that we saw the day of the Festival of Frequency Measurements. Now this is before I got my GPSDO. So there could be I worked very hard to calibrate it. You know, I looked at the 5 megahertz WWV during the day when things are quiet and steady, and that's how I set it. I used daytime WWV is a calibration standard, but it is what it is. The path is Fort Collins down to near San Antonio, and this was at 5 megahertz this time. So here's the spectral plot taken right off of, this is a spectrogram right off of Spectrum Lab. Here's nighttime over here. This is from 10 Zulu up to 15 Zulu. Sun starts coming up right in here. Nathaniel identified a traveling ionospheric disturbance over here. Interesting in its own right, but dang unhandy to be happening right now. I really could have done without it because it complicates this picture. So to get this data into Excel, I loaded this into a program that gave me cursors like Windows Paint so I could read the crosshairs and digitize it manually. And that's this curve over here. And I did all 3 of the apparent curves here. Actually, if you get right down to it, there's more than 3, but there's this mode, which I call mode 1, the one that had been going on all during the night, and then changed with a positive swing at dawn and then settled back down. My best guess is that that's a 1 bounce off of the F layer. There's this other mode that is a higher overtone that if you look at it enhanced version, it was really there before it got bright, but just very weak. So there was some enough refraction to make that mode happen. What's the difference between these two? I had about a 50 dB dynamic range on Spectrum Lab, so that's 50 or 60 dB of amplitude difference. But nonetheless, there was enough there to digitize, and I'm gonna foolishly claim that to be a 2-hop mode, and that's this orange line over here, just digitized from here. And then this straight line that just doesn't move much, I think is the E layer return, which didn't show up till we had enough ionization to make it happen. And then during the day, it just flattened out. Another hint that may be the E layer is that during the day, between absorption in the D layer and refraction at the E layer, 5 megahertz can't see the F layer. And I think that's why it's so flat. So anyway, there's all 3 of those. And the first one I analyzed, of course, was the primary, the 1-hop mode. Did the same thing, converted the Doppler shift mode into velocity, path velocity with this gray line, then did the cumulative sum integration to turn that into change in path length. That's the scale that's over here. That's this blue trace. Here's the effect of this traveling ionospheric disturbance, which served to raise the layer height by about 30 kilometers in the pre-dawn hours. Then the sun came up, the ionosphere lowered. Here it comes. We had a positive Doppler swing, and here's what the change computed. Change in ionospheric layer height computed from the Doppler swing. Going back through the model, and I did the same thing for the overtone thing, calling that a 2-hop mode. Went back to that model, computed layer height from 1-hop, layer height from 2-hop using a 300 kilometer starting point. And they're not exactly congruent, but for as crude as this is, at least they're going the same direction. There's some congruence there. They don't wildly differ. Feeding the 1-hop mode through the 1-hop geometry did this. Feeding the 2-hop data with quite a bit more Doppler shift through the 2-hop geometry came up with that. We did have some ray trace simulations for that day. Unfortunately, the scale factor wasn't particularly good here. You can see that when things got really interesting, the 250 kilometer altitude max over here wasn't enough, and the apogee went off scale above, and you can't really measure how high it actually got. This is one of those graphs that we need to try and get a better handle on. This is what the F layer was at 1350 Zulu, which was right before this mode disappeared. It's about 180 kilometers. And then it disappeared at 1355 Zulu. And then after that, things got quiet and only the E layer remained. Here again, notice what the E layer is doing. It didn't exist nighttime before pre-dawn. When it shows up, it's here, about 100 kilometers. Much later, it's still there. F layer is changing like crazy. E layer doesn't care. So David, you once likened some of this Doppler stuff to flying an airplane in smooth air and in calm air. Well, there you are. The E layer is the calm air and the F layer is the turbulent air. At least that's what it looks like. Okay, the next thing I want to blend into this mix, because it sort of ties in with it, are the time of flight measurements taken back in January of, well, just about a year ago, as a matter of fact. This again is from Fort Collins down here to near San Antonio at 5 megahertz. If you might remember, WWV has these timing ticks that they do every second. Gosh, I can actually play that, I think. You hear the tick, tick, tick. And that's what we're talking about.
At the tone, 12 hours, 2 minutes, coordinated universal time.
What those ticks actually are 5 cycles of a 1 kilohertz tone for WWV and 6 cycles of a 1200 hertz tone for WWVH. The cool thing about it is a GPS DO has a BNC jack on the front that is marked 1 PPS, and the rising edge of that pulse is aligned with the instant that this pulse leaves the radio tower in Colorado. So if you sync your scope off the leading edge off of that 1 PPS pulse and then measure the this 5 cycle burst, you can get the time delay directly. You do have to calibrate out the propagation delay through a receiver, especially if it's an SDR type receiver, because it's a lot. It's as much as the whole propagation time is. It's like 4 milliseconds. But here's a frame capture from WWV and a lot longer later one from WWVH. Of course, it's coming from Hawaii, so it's delayed by that much. You might have heard both the male and female voice announcements for WWV. 5 megahertz was hearing them both. So here's the pulse from WWV, and a little bit later is the one from WWVH. This one was at 10 megahertz. So going back to that model, calculating the time spread of arrival times for the different 1 hop, 2 hop, 3 hop modes, you find out that the differences are like a few milliseconds, 1, 2, and 3 milliseconds. But the pulse is 5 milliseconds long. That means that the higher order modes, more hops, come down while the initial pulse is still going on. It comes down on top of them and they superimpose. So you wind up with a superposition. So here's simulation. Here's a 5 cycle pulse, and a little bit later, 1 millisecond later, here's the same pulse. You add them together and you wind up with a 6 cycle pulse. Can you measure those on the air? Yep, here it is. So there's a 1 hop mode and a 2 hop mode at the same time. If you delay it more for the next hop, you get same thing. The front of this pulse is coming from the first hop. The back half is coming from the second hop. And the stuff in the middle is superposition. There's one of those captured on the air. And you can keep going. There are actually some 3 hop modes, I believe, because that predicts 8 cycles. And sure enough, there's an 8 cycle pulse. So I took a bunch of this data on this one particular day, just sat in front of the radio for 4 or 5 hours and did screen captures on that scope and calculated the time delays. Here's the primary, the 1 hop mode. And remember, you measure that by the leading edge of what you see, because that's the one that gets there first. And then you infer the other ones by the trailing edge, because they get there second. So this is the straight time of the first one, and this is the time delay of the second and third. I just took these numbers and scatter plotted them all at once in Excel, and they clustered all by themselves like this. So I drew lines through them, and sure enough, it really does kind of look like this is 1 hop, 2 hop, and 3 hop modes. Then you go to compare this to this picture which was the computed 1 hop and 2 hop and 3 hop time delays, time of flight versus reflection layer hop. I took that data I measured, smoothed it by interpolating between the missing values so that Excel could draw a trend line, and it drew these trend lines. And then if you take this curve and flip it and then scale it to overlay it on top of this curve, it's not bad. All I did was take this curve, flip it so that the numbers, got smaller or bigger with time to match the this calculation, get the cents going the right way, and then scale it. Anyway, that's kind of cool. That was so cool, I wanted to watch it again. So at this particular height, now, this would not match up if I moved it to the right more, and it wouldn't match up if I moved it to the left more, but at this particular height, at 250 kilometers, the time spread between these clusterings pretty well matches that model. Of course, the axis over here is layer height in kilometers, and the axis on this is time. And during that morning transition, the layer height is indeed changing with time. So that seems to be an additional point in favor of this model making some sort of sense, because they do tend to agree. This is that same thing, a little more spread out, taking this one and laying it on top of that one. They really do match up pretty good, except for these ones that are way up here. The 1 hop, 2 hop, and 3 hop, they look better than they have any right to be. This stuff up here, who knows what that is? Maybe it's 4 hops, probably not. Maybe it's a Pedersen ray, who knows? Maybe it's a return, a ducted wave that got trapped between the effing layer and made extra hops. Who knows what it is? But this particular day, there was some, not long delayed echoes, but longer delayed paths. We did take those actual times that we measured. Nathaniel and Carl provided me with ray trace data for 1, 2, and 3 hop modes, so we could spot check that data. So here's the FARLAP data Nathaniel sent me. Here's the actual pulse that was within minutes of the time he picked. Here was his graph, and my data point sat right there. Not bad. Here was the FARLAP for 2 hops. Here's the ground range and the group delay. Here was the primary, or the leading edge for the 1 hop, measured at the leading edge of this pulse over here. And here was the trailing edge to get the 2nd hop over here. And those matched up pretty good. And then here's a 3 hop mode that Carl gave me using PropLab 3, Pro 3. And gosh, I can't read the numbers. 6.46 is what this modeled, and I measured 6.38. Okay, is there more? I thought there was more. There it is. Okay, so anyway, some conclusions that are suggested by this data, inferences, if you will. The observed Doppler associated with eclipse and the morning evening transitions, they come from the time derivative of the layer of the change in, the layer height, ionization layer height. You get a positive shift for descending ionization and a negative for descending. Whoops, I did descending twice, for ascending. You do the inverse integration process on the measured Doppler data, and you can get back to predict what the change in height had to be. If you combine that calculated data with ray trace modeling, and you have to have a geometric model because you have to be able to go between path length and height, it showed results which were pretty consistent with the premise that higher order modes during the mode splitting really are from multiple hops, at least some of the time, not all of them are. We've seen some really wild behavior where there's like asymptotic frequency excursions that may or may not line up with the asymptotic rise in ionoson data. No, it may be happening. It may be that the critical frequency happened to be near WWV right at that particular time. So the time of flight measurements were also consistent with this premise. They tend to reinforce each other. Multiple data sets suggest height changes, Doppler shifts, and other frequency turbulence effects occur in the F layer. In contrast, the E layer shows height stability, even in the face of an eclipse and diurnal transition periods. So signals that come from the E layer show really profound frequency stability. Here's another graph that Carl gave me that kind of shows a time sequence of what happens on a morning transition. Here's the E layer things here. Here's the F layer things here. His progression indeed shows the negative slopes that cause the positive frequency swings. Here's the E layer, not doing much of anything, just going along for the ride, not changing height, while these F layer slopes are changing like crazy, or F layer heights are changing like crazy, I should say. One last comment for this frequency changes, Doppler changes, and turbulence happening high in the ionosphere was this simultaneous 3 frequency plot of WWV at 2.5, 5, and 10. So what you notice, this is nighttime down here. Here's the morning transition at dawn, and then here's daytime. So at night, all 3 of them are turbulent, lots of selective fading going on, ionosphere is moving all over the place. Dawn happens, everybody swings to the right, and then after you're into daytime, 2.5 and 5 go dead quiet. I mean, they are stable. And that ties in with they come from the E layer, which doesn't change height. I mean, it changes height changes to make all this jitter in here or something, but not the E layer. It's the Rock of Gibraltar going through here. 10 megahertz, on the other hand, was turbulent both night and day, but it's 10 megahertz. 10 megahertz can punch the E layer and make it to the F layer during the day. 2.5 and 5 can't. So that's just another thing that supports the premise that these straight line parts here come from the E layer.
Excuse me, Steve.
Yeah.
On the 2.5 and 5 megahertz, were you actually hearing any signal from WWV during the day?
Yes, I copy WWV typically all day long, and it depends on the day. As you saw, WWV at 2.5 megahertz faded out, and it just sort of skipped here. On some days I can hear it all day long, other days I can't. 5 megahertz, I can hear it all day long, almost always.
Okay, I can't hear it on 5 megahertz during the day. Okay, you're closer than I am.
Well, it's, what was it, 850 miles, 1,350 kilometers.
Okay, thanks.
I have to admit that my ham radio installation down here is not modest. I've got pretty good antennas. So anyway, what it all boils down to is this picture here from ARRL that is a model of propagation that shows E layer and then 1 and 2 hop modes from the F layer. And what this data suggests to me, the hypothesis, the conjecture is that this straight line stuff is from the E layer for all the reasons I've mentioned. This first swing is a 1 hop refraction off the F layer, and the higher order is a 2 hop. And that's kind of what this data says to me. Maybe baloney, but that's kind of what I'm seeing in here. Is that all? Yeah, that's all. So that's the bottom line. That's why I put all these things in here, Nathaniel, because they all kind of point to the same thing.
Yeah, I think that makes a lot of sense. I guess one thing that kind of strikes me, I was thinking about it, is, you know, how do we know that like if you have a 2-hop mode, how do we know that they're both refracting off of essentially the same height? I guess we probably can't actually figure that out.
Well, this is a pretty good clue.
Yeah.
The fact that the time of flight data
Matches so well.
matches so well with what the geometric model said. And the experiments that we're talking about doing, where we get on symmetrical, we put transmitters and receivers symmetrically disposed about an ionosonde, and run this test so that our apogee on our HF path is directly over the ionosonde. Now, if we measure frequency shift during the transitions, we can compare the inferred height layer changes to what the ionosphere actually measures at that frequency. The reason I thought of that in the beginning was to try and either prove or disprove that this is all layer height, or maybe wave velocity played some part in it. Clearly, if the ionosphere measures a change in layer height and the Doppler gives the same number, well, it's all layer height. If they differ, then some of it has to be coming from someplace else. And by the way, from my place down here and the Austin ionosonde, the symmetrical point comes down kind of between College Station and Belton, Texas. So Texas A&M University isn't far off. It's a little too far south and a little too close in, but it's not gonna move the intersection off by more than 50 miles or so.
Yeah.
So if we could get the guys at A&M to play with us, we could
Yeah.
actually do that test.
And you haven't heard from them yet, have you?
No, I wrote them. I haven't heard from them.
Yeah. Are there any questions from other people on the call?
Yeah, I have a question. That yellow data that you have right above, I
Yeah.
can't really tell on the right-hand plot whether it's, you have your 1-hop, 2-hop, 3-hop. I can't see that legend. Could you please specify that?
Are you talking about just this one up here? This yellow line way up on the top?
Yes, that is correct.
I did not, on this particular graph, I didn't have a 4-hop mode, but there is one, and it does kind of come up. I should have, dadgummit, I picked the wrong graph. It does kind of come up there. These could be a 4-hop, but you notice that there's no slope to them in particular. These slopes, not only do they happen at the right timing, but they have slopes that match up pretty well. This one doesn't. There could be some 4-hop modes in here, but I'd bet dollar to donut that there's other mechanisms going on as well.
Could that be a long path?
No, these were still in the order of 5, 6, 7 milliseconds, and long path around the world.
Yeah, longer.
I mean, Hawaii is 17, so this would be 30, 40, 50 milliseconds.
Okay.
It couldn't. Easy enough to separate WWV and WWV8s on timing because they're 17 milliseconds apart.
Yeah, that is a really nice technique. And I think it's really neat how you're able to back out which mode, whether it is likely 1-hop, 2-hop, or 3-hop from the WWV data.
Yeah, and actually, Steve, you get even better than what you're describing for examining WWV and WWVH separately because their pulses are on a different frequency.
Right.
The other thing you're getting from this, Steve, is, you're essentially with the 1-hop, 2-hop, 3-hop. I mean, that's basically giving us a way of estimating the ionospheric height.
Right. Oh, that's right. You could play the differential game. Get an absolute reference that way.
Yeah.
Good thought.
And actually, the first time you sent this to me, that was like one of the big things I got out of it was, I was like, if you do this right, you actually now have a way of backing out what the actual height is.
You do. That's what we should do if we can do the symmetrical ionosonde experiment.
Uh-huh.
Then
I
ionosonde is ground truth.
I do want to give a little warning here. I have to, you guys can stay on, but I'm going to have a hard cutoff just a couple minutes before 4 because I have another telecon that I have to be on. But so I have another like 6 minutes here. But yeah, that's having that technique for backing out the estimated height, knowing which hop it is and what the estimated height is, that's a really big deal.
Nathaniel, quick one thing before you have to leave.
Yeah.
After this morning's telco, I hooked up the Grape to my other Raspberry Pi that has GNU Radio and DRF on it. And I was able to get the Grape to spit out digital RF spectrum files just by plugging it in. And I created a new GRC that contains the right decimation and whatnot. So that plan that we talked about this morning looks workable for the Grape in Antarctica.
That sounds really, really good.
So
yeah, because we desperately need that actual spectrum data out of there. That's excellent, Bill.
So I'll collect a little bit more data, characterize it, and take a look at it, and see and make sure that it looks realistic. But it certainly looks good on the waterfall, and well, I don't have much 5 megahertz signal here to work with, so it's kind of mushy. But when 5 megahertz comes in tonight, I'll take a look at it and verify that we can get spectrum data and maybe run some of the DRF spectrum analysis tools on it and verify that it looks good. So
sounds good. Christina, is there anything else you want to ask about Steve's presentation right now?
Not right now. I think we'll get to it later.
Okay. So yeah, yeah.
I've got a question.
Yeah.
If we could go back to where you're figuring out the envelope data, I'm curious. Why is the Doppler shift, the raw Doppler shift, so spiky?
Oh, yeah. That's Nathaniel and I have thought over that. This data was taken by WA9VNJ. And if you read this, and this is data from his PowerPoint presentation. And in it, he gave what radio he used, said that he was using Spectrum Lab plus custom DSP software. That's it. That's all I know. That's all that was there. So my pictures from Spectrum Lab don't look like this. They're not spiky. You saw what they look like. They're continuous spectra. So all I can guess is that he had maybe a peak detecting algorithm, and the data wasn't present all the time, so it missed a bunch of it. Or maybe it was a threshold effect. Maybe it was a peak detector with a threshold. And if it didn't make threshold, it didn't get recorded. I don't know, I'm guessing.
I think we have his raw wave data from that experiment. So I think what we're going to have to do before we actually write this up, or as we write it up for publication, is we're going to have to go through there and reprocess it from the raw wave data.
Yeah, I'm in particular wondering because in our AM Doppler data, our student has developed a tracker for the Doppler data. And we don't see this kind of spikiness. There is some variation and there's noise in it, but I'm really curious why it keeps returning to 0, so to speak.
David, one of the things that I've seen in my own lab, because it's polluted with 10 megahertz, is that if you have something that's looking for the strongest signal, it will sometimes pick up the signal it's getting off the antenna. Sometimes it'll pick up the 10 megahertz noise in the room from the equipment, and whatever happens to be strongest, and so you'll get this effect.
Right. Well, maybe that data is polluted with a local 10 megahertz.
Could be. I mean, because that will cause this. I've seen
Right.
it in my own lab. So.
Okay,
I've
everyone.
just posted a link to the original data set in the chat if you want to take a look at it. It's in there.
I need to run. I'll make Christina. I'll make you host. And
Okay.
And then you can, if you need to run, you can pass the co-host or the host off to whoever you want to pass it off to.
I will do this. Have fun.
Thank you. Thank you. Thank you,
See you
Steve.
later, Nathaniel.
Thank you, Christina. Thank you, Bill, and everyone else in the group.
Thanks a
Take
lot.
care.
Very interesting.
7-3, everybody.
All right, so I'll bring one up for the RF circuits guys here. At the